Good morning. Welcome to beautiful Barcelona. So it's my pleasure to introduce here today Jeff Dean as invited speaker. Jeff was born in Hawaii, and during his early years, he spent childhood in many places, from Minnesota to Uganda, Atlanta, back to Africa, Seattle. Then he settled in the Bay Area. Jeff is an extremely good engineer, great vision, big dreams, and he pushes his dreams to a very high scale. In Google, every time that you get a new engineer, Jeff is the target. Jeff is the very high level model of accomplishment. He's also a very easy person, very easy to get along with, and a very good team builder. With no further delay, Jeff Dean.
I'm going to talk today about building large-scale retrieval systems, something I've been doing for a little while at Google. And one of the things I like best about this area of work is that it provides a challenging blend of both unsolved research problems that we really don't know how to solve, interesting directions that this work can go in, and it also provides a bunch of challenging engineering problems. And it's this blend of problems that I think is both very interesting and challenging. It also spans a lot of different areas of computer science, which I think is fun. You get to collaborate with lots of colleagues who have different areas of expertise. And it's helpful when you sort of expand your horizons and learn more about an area you may not know much about. When I started at Google, I didn't know much about machine learning. I've been able to work with experts in machine learning and pick up a little bit of tidbits on the side. It's fun. And the scale of the systems we're building is a lot larger than most other systems that one can work on, and so that's always fun. And another nice thing is that I think small teams are able to do pretty significant things that can be used by, for example, hundreds of millions of people. And that's a true testament to the power of software. That's why I love this field, because your work can be used by lots of people. Okay, so when you're building a retrieval system, there are lots of different parameters that you might need to consider. For example, you might have some target of number of documents you want to index in your system. And maybe you have some target goal of number of queries per second that your system needs to be able to handle. You want to be able to update documents at some rate. Maybe you'd like to update 10 documents a second. Maybe you'd like to be able to update 1 billion documents per night. Those sorts of things. You'd like to respond quickly to users. You need a certain amount of information to be kept about every document in your index or other data structures that you're going to be using for running retrieval algorithms. And then you have some either simple or fairly complicated retrieval algorithms you're going to be trying to run on this system. And all of these factors and parameters contribute to sort of the difficulty of the engineering task that you're faced with. If you have small values in all the dimensions, it's not that challenging. If you have very large values in all the dimensions, that increases the engineering challenge significantly. And it's kind of equivalent to the product of these things. It's easy to have a very large index that you never update. It's harder to have a large index that you update all the time. And these all affect both performance of the system, and what you really care about as an engineer is performance per unit hardware cost or something like that. Okay, so just to give you a sense of the scaling of these parameters since I've been at Google, I joined in mid-99. I'm going to give you a rough sense of how these parameters have scaled. So when I joined, we had an index of perhaps a few tens of millions of documents, and today we have many billion documents. So that's 100x. Queries processed per day, 1000x. Per document info, this is kind of a rough measure, but we're basically keeping a lot more information per document that we can use to do ranking than we did 10 years ago. And our update latency, this was kind of surprising to me when I made this slide. It's actually gotten better by a factor of about 10,000. We have some pages that we update in our index within a minute or two, and it used to be we would kind of push out a batch update of our whole index once every month or two. And while all these parameters have been changing, we've been able to drop the average query latency significantly. Now, of course, we've been helped out a little bit by Moore's law and by a larger capital budget these days. But you notice that the improvement in hardware resources has not really kept up with the changes in all those parameters. So that's just to give you a sense of the rough scale we're talking about. The other thing I think is illustrated by the previous slide is that all these parameters change constantly over time. You're always getting more queries per month than you did last month. You're always wanting to index more documents than you did yesterday. And the important point to make is that the right design at a given value might be the wrong design, very wrong, when that parameter scales by a factor of 10 or 100. So a good rule of thumb I like to use is that whenever you're designing a system, you want to think about what would happen if that parameter scaled by a factor of, say, up to 10. But beyond that, it's really difficult to sort of have the same system work for X and 100X. So at that point, you're probably going to need to sort of redo significant pieces of the system to deal with 100X more queries or 100X more documents that you're indexing, because the same designs may not make sense anymore. The other cool thing about web search or search in general is that you can sort of replace the entire back-end serving system without users really noticing. And we've done this many, many times over the last 10 years or so. You can sort of devote a new data center or convert one existing data center to a completely new serving system, run some fraction of your user traffic through that for a while. And once it seems to be stable, then you convert over all the other ones, and users, depending on how visible the changes are that you're making in the retrieval system, sometimes it just seems faster to users, sometimes it just has a larger index, but other than that, it looks pretty much the same with the same user interface. So that's kind of nice. It also allows you to roll back if something goes badly, which is kind of nice. So in the rest of the talk, I'm going to give you sort of a sense of some of the evolution of our searching systems, sort of the internal details of it. It's going to be focused more on the system design as opposed to the ranking algorithms. I'll give you a brief description of some of the supporting infrastructure that we've already published papers about, just to give you a sense of the tools that we use to build some of these retrieval systems. Obviously, anything that covers something of this scope is joint work with many, many people. I've started to try to put a slide together, but it's way too many people to put on the slide. But there are numerous people involved in this effort. And then I'll give you some thoughts about interesting directions and challenges in what I see sort of the next few years. Okay, so as many of you probably know, Google started as a research project at Stanford when our founders were grad students there. I guess their advisors were mean and wicked and wouldn't really give them computing hardware, so they actually had to go beg and scrounge computing hardware from other research groups. They would sneak down to the loading dock and intercept the shipments of computers that other research groups had ordered and volunteer to set them up, and then they would kind of keep the machines for a little longer than they really needed and live off the float of other research projects arriving hardware. So that's sort of the origins of Google. It always started out as a whole bunch of machines kind of connected together by networks. One problem with this approach is that you end up with a variety of different computer architectures. It's not really so pleasant to deal with 5 different CPU types in that environment. So we've standardized on less than that. But the original research project had one, one of the things that it did was they knew that the system they wanted to build was going to be building indices that are way too large for a single machine. And so they started off partitioning both the index and the other aspects of the system across multiple machines. And this is obviously something we continue to do today. That's basically the simple architecture of the research project. Let me talk a little bit about partitioning. So in an indexing system, there are 2 main ways that you can imagine partitioning index data. The first is by document, where you essentially chop the documents you're going to index into a bunch of buckets. And each of the buckets is going to have all the information for some of the documents. So that's nice because each shard basically has all the information for some of the documents and can process queries independently. So you send the query to all the different shards, they send the results back, and then you merge. The nice thing is that the network traffic in this approach is fairly small. So you send the query down to each of the shards. Query's pretty small. They do a lot of computation over a lot of local data stored on disk. But then the data they send back over the network is also fairly small. It's sort of a collection of documents and score pairs. A drawback of this approach, though, is that you often end up doing order k times n disk seeks, where you have a k-word query that you're sending to n different shards. So as the sharding in your system, as your index scales and your sharding gets larger, you start to do more and more disk seeks in this approach. And another drawback is that the query basically has to be processed by each of the shards. That's why the n term exists in that. And it's worth saying, if you drop one of the shards, then you're likely going to be dropping good documents, especially if the number of shards is not too large. The other approach that you could do is you could shard your index by word, where you essentially build inverted indices, and then you give some of the words to one machine, some of the other of the words to another machine, to another partition, and then has the nice property that a k-word query is handled by at most k different shards. And you do only order k disk seeks for a k-word query. The drawback is that you're ending up with the information about each document spread across many different machines, and that you need much higher network bandwidth across because you're streaming posting list data from one machine to another. And it's also harder, there's not an obvious place to have per document information. You might want other information like page rank or the language of the document, other kinds of things that you want to use during ranking doesn't have an obvious home. So in our computing environment, where network bandwidth is a fairly scarce resource, we end up partitioning by document, and that's what makes more sense for us. Okay, so the basic principles in most indexing systems are you're going to assign small integer identifiers to a document. It's good if you can order the assignment of identifiers to have smaller numbers be more important or better quality documents in some sense. That allows you to stop early. So if you retrieve 1 million results and you haven't hit the end of the index yet, you can stop and be assured that you are going to score the 1 million most important documents or highest quality ones. The interface to an index server is given a query, return a list of score and document pairs. In our case, they're sharded by document. The cost of the index serving system, which basically returns scores and document ID identifiers, is order number of queries times number of documents in your index. And then the doc servers, one of the things that the original research project did that most other search engines at that time were not doing is returning query-specific snippets. So when you show a summary on the result page, the original Google prototype would show the title of the document and then some sampling of sentences from the document that were in the context of your query, as opposed to a lot of other search engines, which at the time would show just the first 20 words of the document. And that's actually a very important thing for improving sort of the usability of your search engine, is to show query-specific snippets, because users can scan a list of results and get a much better sense of whether that document is relevant to their query or not without actually having to click through to the document. But it's worth saying that the doc serving system that generates the title and snippets is only going to be order number of queries, not order number of queries times the number of documents in the index. So as your index gets larger, the cost of the index serving portion dominates. And so we don't focus very much at all on the performance of the doc servers other than trying to reduce their latency. Almost all the performance implications in the system are in the index serving system and the ranking system. Okay, so we knew when the company was started that we wanted to ride the commodity computing wave, where cheap commodity hardware was the way to go, so that you could have larger indices, you could afford to devote more computational resources to each query, and so on. So we pushed this a bit to the extreme in the early days, where Now, we actually decided we didn't need all these fancy computer cases, and it'd be better if we could share a power supply between 4 machines so that we didn't have to pay for 4 power supplies. And we would buy all our own components and assemble them ourselves. And so this was our first attempt that involved, there was a cookie tray there, and on top of that cookie tray is 4 motherboards with a thin layer of cork to protect the cookie tray from the motherboards. They're affectionately known as cork boards. And there's, you can see 4 reset switches in the front and a shared power supply. It turns out sharing a power supply between 4 machines is not really that great an idea. We have dispensed with that idea. Nor is cork a good idea. So the serving system in '99 looked pretty much like the original research prototype with a few additions. One is it was replicated more, so each of the index shards and each of the doc shards had multiple replicas on different machines to have capacity. We added an ad system. That was actually the first thing I worked on at Google, was to build our initial ad system. And we added caching to cache common query results. So let me talk a bit about caching. Cache servers are really important pieces of a retrieval system, especially if you want to if you have large query volumes or you want low latency or both. We use them to cache both the index results and the snippets. You get hit rates on the order of 30 to 60%. It's not like CPU caches where we're getting 99%, but and a lot of that hit rate depends a lot on how frequently you're updating the index. The mix of query traffic, is it all in different languages or is it mostly in a small number of languages? How much personalization are you doing? What are the key, if the cache key has to include, aspects of information you're using in order to do personalization, then that sort of takes what would be one simple query's results and spreads them over all the different kinds of things you're using to do personalization. But the main benefits are performance. So you have perhaps tens of machines that are doing half the work of your retrieval system, and the other half is being done by hundreds or thousands of machines. So it's definitely a good deal. You should have caching in there. It also is really nice because it gives you reduced query latency. Time for cache hit is much lower than the time for to actually go out to all the index servers, do ranking and retrieval, and return results. And it also tends to be the queries that hit in the cache tend to be the more expensive queries. They tend to be ones with more popular words in them or popular phrases that are expensive, and they have a lot of documents to score. So even more than just cache hit rate, the cost of the queries that hit in the cache is larger than just the cache hit rate. One of the things to be aware of when you introduce caching into the system is that you can get big latency spikes or capacity hits when the cache is flushed, for example, or when you switch over index data to so that the cache no longer applies and you end up getting a lot of cache misses. Essentially, all your cache hit rate will drop to 0 and then start to work its way steadily back up. But in the moment after it drops to 0, you can have kind of operational disasters. So you have to be kind of aware of that. Okay, so the crawling system around 98 to 99 was a fairly simple batch-oriented crawling system. The idea is you start with a few URLs. Actually, it turns out you need remarkably few seed URLs because most things can be reached from just a few places. You crawl some pages, you extract new links from those pages, you add them to a queue, and you stop when you have decided that you've hit your budget of whatever you can index. There are a lot of concerns in building a crawling system. I'm not going to focus on them too much, but you need to not hit any site too hard. You need to prioritize among the uncrawled pages so that if you have fetch bandwidth available, you fetch something that you think is more useful than a random page. You need some way of maintaining this uncrawled URL queue efficiently because for every page you crawl, you're extracting perhaps 20 links and having to insert them into the queue. And you don't want to do a disk seek for each one of those. And you have to have some way of dealing with machine failures in the crawling system. The indexing system in those days was a fairly simple batch indexing system. It was based on fairly simple tools. There wasn't really any checkpointing, so machine failures were pretty painful in those days. And not only did our early machines not have ECC memory, they didn't have parity, which is very painful if you're trying to actually use them. In particular, if you sort a terabyte of data on a machine without parity, it ends up mostly sorted. If you sort it again, it's mostly sorted some other way. One of my colleagues likened this to programming with adversarial memory. And so one of the early things we did to help insulate us from the adversarial memory was we developed a little file system abstraction that had the ability to write records, and it would checksum them and insert sort of resynchronization markers in there so that if you it would insert checksums in the record so you could know if it was corrupted, and you could also then resynchronize to the next valid record with the resynchronization markers and ignore the corrupted records. And one of the nice things about web search is that there's enough data and redundancy in the world that if you drop, a document here or there due to corruption, it's not that big a deal, generally, unless it's something really important. So index updates in those days, the basics, well, they happened infrequently, thank goodness, because they were a lot of work. They happened about once per month, so you'd basically wait until traffic's low, you'd take some of your replicas offline, you'd copy the new index to these replicas, and then you'd start new front ends pointing at these replicas and serve some traffic from there, and you'd gradually migrate more and more of your machines to serving the April index instead of the March one. One of the things that's important in a disk-based index is you want to use the outer part of the disk because it's faster. So the index switchover process is actually a little bit more complicated. You'd start with the current index on disk, and then you would switch over to the new index by copying it to the free half of the disk. Then you'd wipe the old index. Then you'd copy the new index back to the faster half of the disk. Then you delete the original first copy, and then that would actually free up some disk space that you could use for building various performance improving data structures in the middle. One of the things we built was something we called a pair cache, which is basically, if you look at commonly co-occurring query terms, we would offline pre-compute pre-intersected pairs of posting lists for these commonly co-occurring terms. They don't have to be phrase terms, they just have to be terms that occur frequently in queries together. So we're not building a phrase index, it's just, Barcelona and restaurants occurred in the same documents. So by 2000, we'd refined our hardware design a bit. We had decided cases were okay again. And we'd managed to get all the connectors on the fronts of the computers, which was good. It was quite painful to reach around the back of the old corkboards to install Ethernet cables. And we were still not owning our own data centers. We were leasing space in hosting facilities, and they charged by the square foot, which was an excellent deal for us. So we would try to pack as many computers as we possibly could and use as much electricity as we possibly could into the number of square feet they would license us. So that was good. They sometimes needed a little extra help with their cooling, so we would purchase fans for them. As a consequence, we also got fairly good at moving out of bankrupt data centers and moving into new ones. And so the nice thing is it's not actually too hard to move into a new data center. You have all the racks all cabled up already. And then you basically have to wheel in the racks and then connect together all the rack switches to a central router, and you're ready to go. So in the period of 99 to 2001, roughly, we were simultaneously having huge traffic increases and huge increases in index size. So our index size went up roughly by a factor of 20, and at the same time as we were having, roughly 10, 15, 20% growth per month in query traffic. And we were also out signing deals. So for example, we signed a search deal with Yahoo to provide their search service, and that doubled our traffic overnight. At the same time, we were actually doubling our index size in the previous few days. It was quite exciting. And the performance of the index serving system is what is really important when you're dealing with this sort of thing. We're continuously buying more and more hardware and leasing more and more data center space. But we basically needed 10 to 30% software improvements every month in order to sort of squeak by in our capacity. Otherwise, we would, end up in a bad state. So the nice thing about this basic structure, I've now moved the doc servers off to the side because they're not very interesting from a performance standpoint. The nice thing is that it's fairly easy to add capacity. You can grow your index by adding more index shards, and then you can add more replicas to add capacity. And if you're growing your index a lot, you add more index shards, and then more index shards, and more replicas for capacity, and more index shards. And eventually end up with a lot of machines, and a lot of shards, and a lot of replicas. But it's a fairly reasonable process to do that. As you do, you don't try to do this in the middle of an index. You sort of say, okay, the next month's index, we're going to do 17 shards instead of 10 or something. So one of the reasons you have to keep adding shards as you increase your index size is that you want to have query response times be reasonably low. And if you make your shards too large, then, well, A, they might not fit on the local disks of your machines, or B, your response time would get too large. And so you need to sort of increase the number of shards in linearly as you're increasing your index size. And it's also possible to get pretty big performance improvements, which we did by writing our own disk scheduling system that was sort of aware of what queries were pending on the particular server and prioritizing reads in a reasonable way. We also focused a fair amount on improving our index encoding, which is what I'm going to talk about now. So the original encoding done as part of the prototype at Stanford was pretty simple. It was actually a fairly simple byte-aligned format. Basically, you'd have a document identifier plus the number of hits encoded in 32 bits, 5 bits for the number of hits, and then 27 bits for the doc ID. And then you'd have 16 bits for each word occurrence, for each occurrence of that particular word, that encoded both the position of the word as a sequence number within the document, and a few bits for attributes of the word, like was it in the title, was it in a big font or a little font, and so on. And for very long posting lists, you eventually want to add skip tables into the data structure so that if you have the word of or something, you have a table on the side that tells you, oh yeah, doc ID 1,000,000 is at offset, 2 billion in your posting list. The byte-aligned format was pretty simple to decode, but it's not very compact, and it actually required lots of disk bandwidth. So we worked a fair amount on our encoding data structures, and I'll give you a brief background on various encoding techniques because they'll be useful to understand the encoding format we used. Basically, there's several different bit-level encodings you can imagine using, which are going to be slower than byte-level encodings. Bit-level things are things like unary encoding, where to encode the number n, you just have n ones followed by 0. Gamma, where you're going to encode some prefix in unary that indicates the length of the number, and then that number of bits. Rice, which is a special form of Golem codes, where you basically have a number, and you have a base that you're going to encode that number in. And in Rice codes, the base is always going to be power of 2. So for example, you encode n divided by, let's say our base is 3, then you're going to encode n divided by 2 to the third in unary, and then n mod 8 in 3 bits, and various other things. So the format we used for a while was basically a block-based index format. So the nice property that this had is, so a word is going to have a skip table, and then it's going to have a sequence of blocks. The skip table is optional, only occurs for a small number of words that are very large, that have a lot of data. So the nice property of this format is that there's a byte-aligned header that has 2 important pieces of information. First is the delta from your current doc ID in the posting list to the last doc ID in this block. And the second thing is the block length in bytes. So you can look at that delta to the last doc ID in the block. If you're trying to go to, if you're at doc ID 1,000, you're trying to go to doc ID 10,000, and that delta says the last block has a delta of 2,000, then you know that this block is not of interest to you because it would only take you to 3,000. So you can just read that header, completely skip over the rest of the data in the block, and off you go. If indeed you need to peek inside this block because you think you're interested in something in the range of doc IDs covered by the block, then there's a few bit level encoded things that tell you the encoding type of the rest of the data in the block, tells you the number of documents in the block, and then we have a bunch of doc ID deltas for the individual documents that are encoded in this block. So the block is going to have n documents and then h hits. And then we have n values, so per document, how many hits, how many occurrences of the word were there per document. That's the next piece of information. There's n of those values, and there's going to be h hit attributes, which tell you things like the font size and things like that, and then the actual positions. So notice that this is an incrementally decodable format, so that if you only care about getting the doc IDs, you can decode just up to the doc ID delta portion of this. And then you might say, gee, there's no, I'm doing an AND query. It turns out, I thought there might be matches in these two blocks for the two different words, but it turns out that, doc ID 17 didn't occur in both of them. So then I can skip all the rest of it. I don't spend any time decoding the hit positions or the attributes or anything like that. If what I care about, eventually you may need to decode all this for documents that you score, but that's a fairly tiny fraction of all the documents that you're examining during retrieval, well, all the posting lists you're traversing during retrieval. So this actually reduced our index size by about 30%, plus it was actually a lot faster to decode than the simple byte-aligned format, because you can often skip 50 documents at a time just by looking at that byte-aligned header. So one of the implications of this ever-increasing index size and thus more shards is that the query cost is increasing all the time, because as you increase the number of shards, you're going to do typically a disk seek per shard per query term. And so as you add more and more shards, even for very rare terms, you're going to do a disk seek on each of the shards. And one of the nice things that happens is as you add more replicas for capacity, your total amount of memory in your whole serving system increases. And eventually you squint at this and you say, gee, maybe I could use all that memory for caching. And so you try to come up with complicated ways of caching commonly used posting lists. And then, gee, you kind of squint at the problem and you're like, gee, I could hold the whole one copy of the whole index in memory across all these machines. Of course, then it'd only have one copy of it, but that would be cool. And that actually changes a lot about how you think about what are expensive things in your retrieval system, what are cheap things. So in early 2001, we rolled out our first in-memory index. So we were holding the entire index of all the data in memory. We changed things a bit. So we took all the machines that were dedicated to replicas in each shard, and instead of them being replicas, they each served a different piece of the shard in memory. So we have these things called microshards, where we kind of chop an existing shard up into a bunch of little pieces. The query now needed to go to many more machines. So rather than going to 50 or 60 shards, it would need to go to maybe 1,000 machines. And so we introduced another intermediate level of server called balancers that would take a query from the web server and then direct the request to all the different shards. I didn't draw all the arrows, but it's actually going to all the different machines in that shard. And the balancer is also responsible for sort of coordinating loading and unloading of these microshards across all the different in-memory servers to do both load balancing, and when one of the machines failed, it would kind of deal with recovery of that unfortunate event. So the two main benefits of this in-memory index are that you get a big increase in throughput and a consequent big increase in performance per dollar. You also get a huge decrease in latency, especially towards the tail of your latency curve. So queries that used to take a really long time, well, here's one example, is circle of life as a phrase query. So this is a very expensive query in a disk-based index system because each of those words is relatively common, but that phrase occurs extremely rarely on the web. And so this query in our old disk-based index system would take many, many seconds and have many gigabytes of I/O. And so it would be very expensive. In an in-memory index system, it's much faster because you end up, well, basically because the seeks are 10,000 times faster. Now, there are some issues that you have to solve if you have an in-memory index system. One of them is that because you're touching many more machines on every query than you were with a disk-based system, you end up with a lot of variance. And that variance can really kill your latency because you essentially need to wait for all the results to come back before you return from the query, before you return results to the user. We had issues with, for example, someone had in our operations group, we wanted to do something every 5 minutes. And so rather than the straightforward cron job that every 5 minutes would wake up on all the machines and do something, it was thought that it would be a bad idea to have them all doing it at the same time. So instead, we would randomize the time that each machine would do its kind of 5-minute activities across the 5-minute interval. The unfortunate thing about that is in an in-memory index system where your query is actually touching most of the machines in your data center, it's actually a bad idea to randomize the time. You'd rather kind of have it be done all at once so that you hurt the latency of a few queries a lot rather than hurting the latency of all queries a little bit. And the reason it hurts all queries a little bit is at any given time, at least one of these machines is doing this random cron job and so is running some sort of background activity that is slowing the machine down. The other thing that hurts is that gets hurt by an in-memory system is availability. Because you have many fewer replicas, typically just one replica in each data center of that document's, of a particular document's index data. There are two problems. One is we occasionally have bugs in our query serving system that cause a backend to die when it receives the query. Maybe it's not even dependent on the particular index data that machine has. Maybe it's just a bug in the query parsing code, something like that. Those are not good in any system, but they're especially bad in an in-memory index system where you, if you have a query of death, you end up killing 1,000 machines instead of just 80. So those aren't so good. So you have to figure out some scheme that allows you to insulate or inoculate yourselves from the effect of queries of death. The other thing that is bad is when a machine fails, you end up having a period where the data that machine was serving is completely unavailable. You don't have any copies of that index data in that data center. So for very important documents, we ended up replicating them in multiple different shards and so that we would be insulated to single machine failures and still have CNN's homepage, for example, when a machine went down. Okay, so over time, we've decided that it was better to build our own data center facilities. This is a picture of our data center in the Dalles, Oregon, near a big hydroelectric dam. And so this is just to give you a sense of the kinds of facilities we're building today. If you look inside, it's still, we're back to no cases. It turns out airflow is better, but they look much cleaner than the cork boards, don't they? So basically, the current machine design is essentially an in-house rack design that provides pretty good airflow, standard PC class motherboards still, fairly low-end storage and networking hardware. They all run Linux, plus a bunch of in-house software on top of that that I'll talk about briefly. In 2004, we rolled out another fairly significant change. It's sort of a generalization of some of the stuff we learned from our in-memory index. One of the things that happened is we sort of generalized the notion of this query distribution tree so that you could have a 2-level or a 3-level tree, whichever made sense, depending on what size index you're trying to serve. We generalized the notion of balancers so that there was one manager for doing load balancing across the entire cluster. There were much cleaned up APIs, so it was possible to basically use this simple, this same basic system and plug in your own scoring function. If you're, for example, implementing a different product at Google, like book search, you want to plug in your own book-specific scoring functions, but you still want to use sort of the nice infrastructure that the system provides. The whole set of APIs were designed so that that was pretty easy to do. By this time, it developed a distributed file system that we could depend on and sort of reliably use. So at the bottom level is GFS, which is this sort of cluster level file system where all the index data was actually loaded from. In the previous systems, we would sort of manually SCP data to local disks. In the new model, GFS is sort of assumed to exist, and you can sort of load index data out of that and so on. What else is there to say? So again, we rethought our index encoding data structures. The block level index format, which we had designed when we were still a disk-based index and sort of still continued to use, albeit with smaller blocks in the in-memory index, used a two-level scheme. Basically, we would encode sequences of doc IDs, and then for each document, we would encode a sequence of positions. And the doc ID deltas, as I said, were encoded with rice encoding. So that's a fairly compact bit level encoding. It gives you very good compression, and the block-based format meant that it was pretty good for, it was fairly CPU friendly as well, because you could often use the block headers to skip things. In our new format, we use a single flat position space, and we have data structures on the side that keep track of these document boundaries. So if you have a document with 100 words, that's going to get allocated positions 0 to 99. And then you have a document with 10 words, that's going to get positions 100 to 109. And you're going to have these other data structures on the side to allow you to keep track of which positions map to which document. The posting lists for each word then are going to be a single flat position list as opposed to this two-level doc ID and position pairs. It needs to be a compact data structure, so you can't really afford 32-bit values per occurrence, but it needs to be really fast to decode. So that's paramount for your performance. So it turns out you want to use byte-aligned encodings and variable length ones for encoding your sequence of position deltas. You obviously always use deltas from the previous position, not the actual position, because they're much more compact, especially for very frequent words. So one encoding that you can imagine using is what I'll call a variant encoding. It's basically 7 bits of data per byte plus a tag bit that says, is this the last value in the byte or not? So for example, if you have the value 1, we're going to use the blue things are going to be the tag bits. And so the value 1 is encoded in those 7 bits, and 0 means that's the last byte in the value. 15 is encoded similarly. 511 doesn't fit in it's bigger than 2 to the 7th, so you need 2 bytes of data. So there's a 1 in the first byte indicating that you have to continue on to the next bit, to the next byte, and get the data from there. And 131,071 requires 3 bytes in this encoding. Wow. So the problem with that encoding is that it requires an awful lot of shifting and masking and branching, especially unpredictable branches, which are very expensive on modern machines in order to decode. So one thing you might try is to take the length of the value that you're going to encode and encode that as the low 2 bits of the of maybe the first byte in the value. So in this case, we have 1, and the low 2 bits indicate 00 indicates it's a 1 byte value, and 01 indicates it's a 2 byte value, and 10 indicates it's a 3 byte value. So that's pretty simple. It's very nice because you have fewer branches. You essentially just load a 32-bit value, look at the low 2 bits, and that tells you a mask value that you can use to you shift the rest of the word right by 2 bits, and then that mask value tells you how many of those bits you should use to decode. So there's no branches actually, which is kind of nice. So an encoding we actually came up with that we're pretty happy with is what I'll call a group variant encoding. So the idea is similar to the previous one. You're going to encode groups of 4 values into bundles of 5 to 17 bytes. So the first thing you're going to do is you're going to pull out these 4 2-bit binary lengths into a single byte prefix. And that gives you the tags. Then you're going to encode the actual values just as either 1, 2, 3, or 4 bytes. So that's actually pretty nice. It's a little bit less compact than the 30-bit and like the 2-bit embedded in the byte encoding, because you'll use an extra byte. It's up to 20% less compact. But to decode this is pretty fast. So you load the prefix byte, that's the blue one, and you use the value to look up a entry at a 256 entry table. And that tells you two pieces of information. First, it tells you the byte offsets of all the different values in the bundle. And it also gives you the masks to use to decode the values. So by doing a single byte load, a single table lookup, you now have all the information you need to decode all the numbers in that bundle. Furthermore, the data dependence chain in decoding those numbers is very short. They're all basically that single byte load plus the table lookup, and then you have all the information that the machine needs to have lots of instruction level parallelism in decoding that. Whereas in the previous approach, you need to decode 2 bits, do some masking and shifting, then go to the next number, decode 2 bits. Anyway, it turns out it's a lot faster. I'm telling you about it, and I like it, so that's why. So in 2007, we rolled out another fairly substantial change, was that we really should have done earlier, but it was sort of an operational and sort of logistical effort to get it done. The main issue was we had our web search product, which had a very large index of web pages, and then we had all these other products that people could go to directly to do, you could go to print.google.com to search books, you could go to news.google.com to search news. And that's really not that great a user experience, because the user has to pick which corpus they think is relevant and then go to that particular property and search it. And so we would sometimes search news when you did a web search and show you an embedded news result if that seemed relevant. But really, we should be searching all corpuses at all times whenever you do a query on Google, so we can find you the most relevant information regardless of what particular corpus it happens to reside in. One of the things that had to happen for that is all the other properties had to be built to have enough capacity to handle full web search query volumes. And that's actually somewhat challenging to do, because a lot of those other products were engineered assuming much lower query volumes. So the print.google.com, for example, was engineered assuming the traffic to the book search system, which is a lot lower than our web search traffic. And so we had to sort of get everyone using a common system that had all the same performance enhancements we'd put in a web search and put them all into the other corpora. As part of that, we built an indexing service, so it was easy for different products to dump data to be indexed into the system. It would get indexed and built. And each of those trees, each of those triangles is essentially one of those corpus trees that I showed you before, with a root and some intermediate servers and some leaves handling that. And then there's obviously lots of interesting challenges in deciding, given the results from each of these corpuses, which ones are most relevant to show for that particular query, and what UI should you use to show them, and so on. I think we in the past had approached this problem as we said, gee, we don't have much capacity. Let's see if we can find some queries that we'd like to send to some of the other corpora that we believe will have good results. But that's a much harder problem, because you're actually trying to decide based on 3 words in the query, is this going to be interesting, will the Google Groups corpus have interesting results for that 3-word query? And that's actually a much harder problem than if you actually send the query down, get the scores back from that corpus and the relevant documents, and then we can make a decision saying, oh yeah, well the score from Groups is 12 and the score from Print is 5, so I'm going to assume that one of them is more relevant than the other. Although the scores may not be directly comparable, you could, over time, over a set of queries, understand, when one corpus is going to be more relevant than another. The other big change that's happened relatively recently is that we now have the ability to update our index in a matter of a minute or two for a given page, as opposed to waiting fairly long periods and doing very large batch updates. And there are a lot of things that have to change in your system in order to really do that right. First of all, how do you know what pages you want to update? It's good to have a system that can identify, are there interesting new pages on the web that have just shown up in the last minute or two? Or are there important pages that have been updated that ideally you'd like to have any page as soon as it changes be updated in your index, but that's a very difficult thing and there's not enough crawl bandwidth in the world to sort of really do that, and some pages change every time you crawl them because they have like the timestamp at the bottom. So you sort of have to pick and choose your battles and decide for a given budget of pages that you're going to update, what are the most important ones that you want to update in so that your index is fresh and useful to users. So the crawling system needs to be able to accommodate these very fast update requests. Like I want to update this page and I want it now, not here's a whole bunch of URLs and I want them, in an hour. The indexing system is challenging because it depends on global information, at least for web search, for example, where you depend on things like PageRank, you depend on the anchor text of pages that point to that page. You need to actually index that data with the target document. So you must have some way of getting this information or some approximation of it in order to index a page within a minute or so. And the serving system has to be rethought a bit so that it can accept updates for different documents while you're actually serving requests and accept updates at a fairly frequent interval. And the data structures you actually want to use are fairly different in that case than something where you update things in batches of an hour or so. The other thing that I think is important and we've realized over time, is that it's really important when you're trying to make progress on improving ranking and search quality and so on, is that you want to make it easy to do experiments. And the faster you can make turnaround on a particular experiment from when you have an idea to when you actually can demonstrate a prototype of that idea, the better it's going to be. So we've spent a lot of effort building tools that allow it, that make it fairly easy to do some kinds of experiments, and that's been hugely beneficial. Some experiments you don't actually need to sort of do very much. You just want to weight different ranking parameters, and those you can actually do without really rolling out anything in terms of new binaries or anything. You can just do them online. The ones that are more difficult are the ones that need information that you didn't have the foresight to build into your production index. So you need some way of computing new information, generating it. Often it involves making a pass over all the documents or over some derived information from all the documents, and being able to build that data structure on the side that you can then use to do your experiment. I'm not really going to talk very much about these various systems, but several of the pieces of infrastructure we've built are useful for doing some of these kinds of experiments. I already talked a little bit about GFS, which is just a big file system spread across thousands of machines. MapReduce is an abstraction that makes it easy to write and run large-scale kind of batch computations. It deals with like nasty things that happen, like machine failures. It automatically parallelizes things across lots of machines. And it enables you to write fairly simple programs that can extract information that is of interest to you for your experiments and perform those ad hoc experiments more quickly. And Bigtable is a sort of semi-structured storage system. Think of it as a very large row and column oriented store. So for example, one thing that gives us is online efficient access to per document information at any time. You can say, what is the current information I know about CNN.com? And it will tell you, okay, the page rank is this, we last crawled it at this time, here's the current contents that we know about, so on. And this is very useful for being able to update documents in a matter of minutes as opposed to days. Okay, so the experimental cycle, you want to start with a new ranking idea. You obviously use these tools to generate interesting data, and then you want to be able to, at first, run an offline experiment. So no users are involved in this. You essentially just want to run your, say, ranking change and look at what effect it has on how results are ranked for different query sets. And some human-rated query sets, and other ones, maybe you'll do a random selection of queries and just look at what changes compared to the production ranking. So the important thing to note here is that the latency or the throughput of this prototype don't really matter. You can run 10,000 queries and it can take hours. That's okay. It's not ideal, but it's okay. And then you kind of iterate based on the results of this. Maybe you find that, gee, it works well in this case, but not this case, and then you change your code a little bit. So the experimental framework, or the experiment that you run must operate at pretty close to production latencies. Adding 100 milliseconds is maybe okay, but adding a second or two is definitely not. Okay, so now you've managed to convince yourself based on various kinds of user quick metrics and so on that your experiment is better than what we're running today. So you want to be able to launch it. And so sometimes it'll just work because you thought about throughput from the beginning. But sometimes maybe you do fairly expensive things that are computationally not so ideal on our full traffic volume. So you'll need to figure out how you can tune whatever it was you did in your experiment so that it can run at full Google.com traffic volume. And one of the techniques you often use is you're going to pre-compute something instead of computing it at runtime. Another one is maybe there's some much cheaper approximation you can use that will be good enough, although obviously then you need to go back and revalidate that your approximation is giving you the same kind of quality that your full computation was. It's really important to have a smooth rollout process for search quality improvements. You're continuously making these quality versus cost trade-offs. You might have some you want to launch that increases the CPU cost of every query a little bit. You need to have some sort of understanding and budget for improving quality. But if you don't, then you're going to have not healthy relationships between the people who want to minimize the number of machines you take and the people who want to improve search results. So having sort of understanding of what are the acceptable CPU costs that you can have this quarter for new quality improvements is a really helpful thing. So, interesting things. So I think we're just starting to scratch the surface at what can be done in terms of cross-language information retrieval. There's been a lot of progress in based translation. We have a research group at Google that is working pretty extensively in the area and is getting pretty good results for sort of automatic machine translation between different languages. The ideal goal is basically be able to translate all the world's documents into all the languages. Obviously, this is good for engineering because it increases index size a lot. That's really good. And there's lots of computational costs just doing the translation the way it's done today. But there's huge benefits if it's really done well. So you can imagine that anyone, no matter what language they speak, can have access to all the information on the web, not just the subset of it in the language that they happen to speak. It's especially important in languages where there's not a lot of content in that language on the web. So obviously there's two challenges. One is continuously making the translation quality better. And there's actually lots of interesting large-scale systems work in the actual translation process itself. I actually worked with them a little bit. Turns out in order to translate one sentence, we need to do 1 million lookups in a multi-terabyte model that basically keeps track of how often every 5-word sequence occurs in all of our documents. And that doesn't fit on one machine, so you end up with this huge lookup that you need to be able to do in parallel across a large number of machines where you loaded your model into memory. Another kind of interesting thing that is happening as we try to sort of have other products like Gmail that is personal information, various other kinds of products like groups that are shared between groups of anywhere between 1 and 1 million people, is how can you actually build retrieval systems that deal efficiently with documents that are private, that are sort of semi-private to fairly small numbers of people, that are shared extensively, or that are completely public like web pages. And the best solution that you can come up with for a given document that is shared with 10 people is pretty different than a very public document. And even worse, the sharing pattern of a document might change over time. It might be something you author first and now you want to publish it to 1 million people or 1,000 people or something like that. So there's interesting things to do there. Another area where I think there could be some work is how can we automatically construct efficient retrieval systems? So currently we have several different subsystems in our retrieval system that are suited for different kinds of information or different kinds of parameters of the system. So one system deals with a small number of documents, but can do sub-second update latencies on those documents. Another one is for a very large number of documents, but deals only with very large batches of updates at once per day, say. So we've made a lot of progress on having common interfaces for the scoring and ranking functions on across all these different subsystems, but the implementation is pretty different. And that works reasonably well. We're sort of happy with it, but it takes a lot of effort to build and maintain and extend all these different systems. So could we have a parameterizable system that, given some information about how many documents you want to update per second, per day, automatically constructs the right mix of retrieval subsystems to build, minimize your machine cost or something. Another interesting area is doing better information extraction from semi-structured data. I think the fully labeled semantic data is pretty interesting, but it's going to be a tiny fraction of data that exists in the world. And there's going to be much more semi-structured data like web pages with tables and so on in them that is going to provide you with a larger set of information, although it's noisier. So how can you sort of improve algorithms and techniques for extracting this kind of information from these unstructured and semi-structured sources? Obviously, there's a lot of redundancy, so that helps you in sort of dealing with the fact that the data is inherently noisy. You also want to be able to combine and correlate and aggregate all these things across different sources. Okay, so in conclusion, it's fun to build these systems. It's really a lot of challenging problems. I work with great colleagues. They're new problems all the time that require sort of continuous evolution of the system built and new directions we want to be able to go in. It's really nice that this work benefits a lot of our users, all of our users. And I think that's probably the most fun that I have is because what we're doing is challenging, useful, and fun. Okay, so thanks for your attention. And I don't know if we have time for questions, but done. Any questions? Okay. Yes. Hang on.
Why do we want to slide every document to all languages? I didn't get this. Isn't this extremely too costly at the end or relatively small gain?
Well, so that seems like a good ideal goal. Obviously, you might make some approximations. Like you might say, okay, I want to take every document and translate it into the 10 most commonly used languages. That would be, not quite as useful, but would be much less costly. So these are the kinds of engineering decisions that you're having to make all the time when building any retrieval system. And I think, you're right. It would be pretty costly to do it that way. But I think it's important to keep track of what the goal is and then figure out how you can sort of meet almost all of that goal in a less costly manner than to say, well, we're not ever going to be able to do that. And oh, well.
So your snippet cluster and the document cluster seem separate. I was wondering where the snippets are actually computed. The index and the
right.
Sorry.
So the snippets are computed in the doc servers. Doc servers basically have access to the full document text that we crawled, and you get a query in and a document ID that says, okay, I want to snippet this query for document 12, and then it goes and fetches the contents of document 12 and computes the snippet. Okay. Thank you.